Hopefully this video comes out the week I record it, or else I would break my promise for the second time in a row. But I digress, and today we're going to be looking at this integral. It is an improper integral, and it's to infinity, and we have a natural log of x times the natural log of x minus 1 over x plus 1. The product of logarithms, and then over the x cubed. This was something I was exploring when I was doing regular logarithm integrals, and it has an interesting solution. It has to do with the Basel problem, if that helps. So let's begin. And the first step, what we're going to do is we're going to make use of a substitution. And the substitution we're going to use for this one is t is equal to 1 over x. Now, this might be rather strange, but just proceed as follows. So I have x equals to 1 over t, dx being equal to negative 1 over t squared dt. And so this would become an integral from 1 to 0 of natural log of 1 over t. We can use the property of the logarithms, and then this would actually be over 1 over t cubed. We can drag this to the front. We have the natural log of 1 over t minus 1 over 1 over t plus 1, and then dt, negative dt over t squared. Okay, so now we can use this negative to switch the order of integration. You can now drag that to the front, and this would become just regular t, and then we have a natural log of t, 1 over t here. Okay, that's fine. So we can drag a negative to the outside, and then for this one, we're just going to expand by 2 over t to rationalize the denominator. So we have negative from 0 to 1. T natural log of t. That is Lm, but I do not care. Natural log of, if you multiply by t, that's going to be 1 minus t over 1 plus t dt. And this right here is going to be our main sort of integral for today. And the original integral is just going to be negative that. So we're just going to start by working on this thing. I would want to erase this because I don't think this blackboard would fit. So, you know what? I'll just erase this and I'll just continue with that. Line. Okay. So we're going to look at the integral from 0 to 1. And I'm going to write slightly smaller. T times the natural log of t, natural log of 1 minus t over 1 plus t dt. Okay, cool. And you can use the property of logarithms to split this up. So we have an integral from 0 to 1 of t natural log of t natural log of 1 minus t dt, and then minus from 0 to 1 t natural log 1 plus t dt. Okay, so that's all cool. Let me actually check if you can see that. I think you can, yeah. So this is what we have here, and now we're just going to calculate these two integrals separately. So for the first one, we're actually going to use the Taylor series for this. So we're going to have a negative on the outside. We have an integral from 0 to 1 of x natural log x. We're actually going to change this to x for some reason. I don't know why. But yeah, and then we have the sum. And it's equal to 1 up to infinity of x to the n over n dx. And then same thing for this one. So we have plus, because minus is plus, 0 to 1 of x natural log x, and the sum, n is equal to 0, no, not 0, to 1 to infinity of negative 1 to the n, x to the n over n dx. And so now we can just drag these sums to the outside, and now if we're going to combine them, these are just going to be x to the n plus 1 times the natural log of x. And here we're actually going to use a formula, which I might actually prove in the future. It's going to be just another simple integral video, a casual one. This logarithm integral can actually be generalized, and we can make use of it. So this is now equal to, if we do this to the front, because I like positives to be at the front, we have the sum, n is equal to 1 to infinity, of negative 1 to the n over n. Now, the formula is this. So we have negative 1 over the exponent plus 1, so that's going to be n plus 2 squared. Okay, that's all fine. And then minus the sum here, which is going to be n is equal to 1 to infinity. That exact same thing, just with the normal n. So we have n plus 1, n plus 2 squared, negative 1 on top. So we can then change the signs, drag this to the front, because we like positives to be at the front. And so now we would get the sum n equals to 1 to infinity n times n plus 2 squared minus sum n is equal to 1 up to infinity of n plus, n times n plus 2 squared, negative 1 to the n. And this is our sort of series right here. Now, we can't really do much with it currently in this form, so we're going to apply partial fraction decomposition, and that should make it a lot easier. So if we're going to partially defractionize just this part, because this thing is just that times negative 1 to the n. So now we're going to look at, and I'm going to switch to my blue pen if I have it. Wait, hold on a second. Okay, cool, blue pen. So for the partial fraction decomposition, it's gonna look like n times n plus 2 squared 1 is equal to some constant a over n plus some other constant b over n plus 2, and then plus finally a constant over n plus 2 squared. And so now we can then look for these couple of constants right here. Now for these two, you know, I won't use that method because it's gonna sound weird to new people of the partial fraction decomposition community. So we have, if we multiply both sides by n times n plus 2 squared, this is just me a times n plus 2 squared. And if we were to multiply the a's in the, no, if we were to multiply out, if we're going to calculate the square and then bring a into it, we have a n squared plus 4a n plus 4a. And then onto this b term, which is going to multiply by n times n plus 2. So n squared b plus n times n plus 2 is going to be plus 2bn. And then lastly, that one is just going to be plus cn. So now we're saying this is always true for all n, so we can compare coefficients. And so you would get 3 equations and 3 unknowns. So first of all, we have the n squared. So we have a plus b, which is equal to 0, because there is no n squared on this side. And then we have the n's. So we have 4a, 2b, and c. So we have 4a plus 2b plus c, also equal to 0. And then, so finally for the constant, we only have this. So we have a is equal to 1 over 4. If you plug this into that, that would mean that b is equal to negative 1 over 4. And then if you plug these two, so it's going to be 1 minus a half plus c is equal to 0. So we have c is equal to negative 1 half. Okay, that is cool. So we have our partial fraction decomposition, which is going to be, is going to be 1 over 4, and then this will be negative 1 over 4, and then this is going to be negative as well, 1 half. Alright, so that's cool. We have our solution, and to save space, because I'm not really sure, you know what, perhaps we're gonna keep it, and we're just gonna take a risk. If it comes that we need more space, then too bad. So we have here, I'm gonna first do this series first. So how we're gonna split this up, we're gonna let this equal to 1 over 4 times the sum, and it's equal to 1 to infinity of n, 1 over n, minus n plus 2, 1 over n plus 2. There you go. And then minus 1 half times, can we fit that? I think we might be able to. The sum, that's a weird sum, and is equal to 1 to infinity of n plus 2 squared. Oopsies, okay, whatever. And then for this other sum, it's just going to be the exact same thing, but yeah, it's going to be basically the exact same thing. So here we have is equal to 1 over 4. Oh no, it's not equal to. It's going to be minus 1 over 4 times the sum, and is equal to 1 to infinity of negative 1 to the n times over n, plus 1 over 4 sum, and is equal to 1 to infinity of negative 1 to the n over n plus 2. Okay, and then plus 1 half sum, and is equal to 1 to infinity of negative 1 to the n over n plus 2 squared. Alright, so that's cool. This is a telescoping series. I think it is equal to 1 minus 1/3 plus a half minus a fourth plus a third minus a fifth. Yeah, I think it's just that first, or is it just 1? Okay, wait, I'm confused. 1 minus a third plus a half minus a fourth plus a third. Oh, okay. So I think it's just 3 halves this one. So that 1 and that 1 half stays. Everything else gets cancelled. So that's that. So 3 halves, so it's going to be 3 over 8. Okay, that's cool. And then this one, minus 1 half. And then this thing is just going to be the zeta minus the, so it starts at 3 squared. So minus the first term minus the second term. So it's minus 1 minus 1 over 4. It's going to be minus 5 over 4. So we have minus 1 half zeta of 2, which is going to be pi squared over 6, minus 5 over 4. Okay, that's cool. And now we have this one. This, I think, is just negative natural log of 2 times that negative, so we have plus 1/4 natural log 2. Okay, cool. Actually, I might think these two will be a telescoping series, but in my calculations, I did not use it, so I wouldn't want to take that risk of trying it now and embarrassing myself, but whatever. Anyway, this part, if I change this to negative and then minus 1, all it's missing now, because it starts at 1 over, it starts at, let me think for a second. It starts at 1 over 3. So it's going to be the alternating harmonic series minus the first term minus the second term. So it's going to be minus, wow, okay. It's going to be minus 1 and then plus 1/4. So it's going to be minus 3/4, I think. So this is going to be minus 1/4 natural log of 2 minus 3 over 4 I hope this is correct. It might be wrong, but I mean, I'm doing this all in my head, so hopefully you will understand. And then for this one, so I can change this to negative and then minus 1, okay? So that's just the Dirichlet eta function of 2 minus the first term minus the second term. So minus the first term would be 1, I think. Yeah, minus the first term would be 1. So 1, and then minus the second term, which is going to be minus a fourth, minus a quarter. So minus 1, is it minus 1? Oh yeah, wait, it is minus 1, and then the second term is going to be negative 1/4, which minus 1 is a fourth is going to be plus a fourth, so it's negative 1 plus a fourth, which is going to be negative 3/4. Wait, perhaps I did this wrong, because it was minus 1, it was minus 1, and then you add 1/2 to that. So it wouldn't be this one then. It would be 1/2. Huh. I told you I would do these wrong. I always do bad at mental math. So I think this is right. So minus 1/2, and then pi squared over 12. And then here it's going to be minus 3/4. I think this is all fixed. I think this is all right. Maybe? I think so. This, I shouldn't do it here because I should actually expand these. So here we have is equal to 3/8 minus pi squared over 12, and then minus is going to be plus 5/8. So yeah, these two just make 1. So 1 here, minus pi squared over 12, and then plus 1/4 natural over 2, minus 1/4 natural over 2, so that cancels. Minus, I mean positive 1/8. That's cool. And then for this term, it's going to be minus pi squared over 24. And then minus is going to be positive, and this is going to be 3/8. Okay, that's cool. So these two will just make, let me actually think. So that would be 2/24, that would be 3/24. That would be pi squared over 8. Okay, pi squared over 8. And then, so these two, it would be 1/2. 1 plus a half is only 3. There's only 3 halves. And then it's going to be minus pi squared over 8. Aha. So very cool. I think I did not do anything wrong, because I remember this was the sort of equation that I got. Anyway, good news is we actually saved a bunch of space here. Yeah, we did not need to erase all that. But, yeah. So, this is now the value for that. And our original integral was just negative that. So we just have to flip these two around. And so we get, finally, this is equal to pi. Oh my god, that's such an ugly pi. Squared over 8 minus 3/2. And with a trembling and unstructured, unanchored finger, box that out. That is the integral for today and this week, or this 2 weeks. If I choose to do a simple integral, oh yeah, I do need to prove this, so I might do a simple integral, because my school is celebrating Dragon Boat Festival, so obviously I get a day off, so I could do that. I could prove that identity in the future. So this could be the complicated integral, and I wouldn't say promise because I might break it, but I would try and do the simple integral, which isn't made that. And I think that is a good conclusion. Feel free to, look at this, take your screenshots, try to understand the calculus behind it, and yeah, I'll say that was a pretty satisfying journey. I'll see you in the next one.